In this section, we'll study orthogonal sets. A set of vectors u1 to up in Rn is an orthogonal set if each pair of distinct vectors from the set is orthogonal. See this example. u1, u2, u3 are given, and we'll check if the set of vectors is orthogonal. In order to do that, for each pair, we have to show it is orthogonal. Okay, now let's begin with u1 and u2. Okay, for this one, if we do dot product, then there is 0. Second component, now minus 2 and plus 2, so that it must be 0. And u1 dot u3, first one is last one, that is minus 5 and plus 4, and the last component makes 1, so again it is 0. Okay, now u2 dot u3, okay, now that is u2 and u3, that is 0, and that is minus 2 and plus 2, so again 0. So each pair is orthogonal, so that the set is an orthogonal set. S is an orthogonal set of non-zero vectors. Now we require extra condition non-zero vectors in Rn, then the set is linearly independent and therefore forms a basis for the space spanned by S. Okay, once S is linearly independent, then the remainder part is quite trivial. So we have to show here the set of orthogonal, non-zero orthogonal vectors is linear independent. Okay. Here, so we start with here the linear combination is 0. Then we have to show that every coefficient must be 0. For example, to show C1 is 0, we take the dot product with U1, then that one will be non-zero because the collection is a non-zero vectors, and however they are orthogonal, so that this quantity up to there, every year, the value must be 0. But this one is non-zero, so that non-zero times C1 equals 0, which means C1 must be 0. Similarly, we can show C2 is 0. Here C2 is 0 by taking the dot product with U2 and so on, so that we can prove all the coefficients are 0. Okay, so that means that this set of non-zero orthogonal vectors is linearly independent. Okay. By definition, an orthogonal basis for a subspace W of Rn is a basis and also is an orthogonal set. Base, but it must be also an orthogonal set. Then we say the basis is an orthogonal basis. This theorem shows one of the reasons why orthogonality is quite useful property in vector spaces and metric algebra. U1 to UP is an orthogonal basis for a subspace W of Rn. then for each y in W, the weights in the linear combination is given by in this way, because you want U2 you want UP forming a basis. Always for every vector y, we can make this a linear combination. This is always true. Now, the coefficients can be obtained quite easily in this way. Here, Cj is u dot uj divided by uj dot uj. So rather than solving the linear system to find the coefficient, we can find the coefficients quite easily by using just twice of dot product. And so that is quite a simple expression, and so that using such orthogonality is a very useful tool in various algorithms in metric algebra. Okay, to find, for example, and Cj, we take a dot product with uj for y. Then, because that is an orthogonal basis, so except the uj, jth term, everything else will be 0. So we have only this one. So we have from, okay, so that from this one, Cj will be decided quite easily. Just that is non-zero quantity. So divided by that quantity, we decide Cj, right? So the proof is quite easy. Okay. Now, U1, U2, U3, in the last example, we show that set of these three vectors form an orthogonal basis. Now, here, and express the vector y as a linear combination of vectors in S. Okay, so that S is the orthogonal set, and we try to express here y equal C1 U1 plus C2 U2 plus C3 U3. We want to express in this way. Now, using the formula, we can find the coefficients weights quite easily. Now, C1 is the same as y dot U1 divided by U1 dot U1. We can express this portion as U1 norm squared. Okay. Now, y and U1, that is 11. Okay, first component, that is 11. And that is 0 and minus 5. Okay? And then bottom is U1 dot U1, 1 for 1. So that is 6. Okay, so C1 must be 1. How about C2? That is again y U2 over U2 dot U2. Okay, y and U2. The first one is 0, second component is 0, last one makes minus 10. Okay, now U2, that is 1 plus 4, there's a 5, so that there's a minus 2. Okay, now the last coefficient, C3, that is y dot U3 over U3 dot U3. Okay, y is here, U3 is here. Now for the first one, from first components, we have minus 55. From second components is 0. And from the last ones, we have minus 5. Okay. Now, the norm of U3, in fact, we have to get squared. Okay, so the 25 4, 1. So that is now 30, right? 25, yeah, that's 30. And this quantity is minus 60, so that minus 2. If you, here that is 1, minus 2, minus 2, then that's the final answer. It's not so difficult, right? Okay. Now we'll define orthogonal projection. Let's see this figure. For a given non-zero vector u, and we consider the problem of decomposing a vector y into sum of two vectors. One is parallel to u, and the other one is orthogonal to u. So therefore, this y, we try to find the parallel to u, this component, and the orthogonal to u, that component, so that y equal y hat plus z, y hat is parallel to u, z is orthogonal to u. Okay. Now, to find y hat, because that one is saying that y hat must be parallel to u, so we may start with that one, right? Okay. Then, now z is y minus y hat is alpha u, so that z is y minus alpha u, and we'll try to use this one, and that must be 0. If we make a dot product, then that must be 0. Z dot u, z is already y minus alpha u, and we expand, then this is known quantity, and u is non-zero, so that this one is non-zero, and so that e equals 0. So we can decide alpha quite easily in this way. Okay, now we'll summarize this derivation into this definition. Given a non-zero vector u in Rn, for y in Rn, we start with this decomposition, and y hat is parallel to u, and z is orthogonal to u. Then once y hat is alpha u, then alpha is determined in this way, we already did, and z will be computed by subtracting here two vectors in this way. Just as simply we move this one to over there. Once it is known, then z will be decided by here y minus y hat, right? Okay. Now, vector y hat is called the orthogonal projection of y onto u. Pictorially, here y hat is the u directional component of y. So it is projection. Okay. So like in plane, once we have a point and over there, then once it is projected onto x-axis, then that is, in fact, if this is a and b, and x direction a, y direction b, then that will be a. That is, in fact, the projection onto the x-axis. Exactly the same way, here projection in general direction u, projection is basically the y directional component of u directional component of y. So that's exactly here projection y hat. And remaining part is orthogonal part here. Okay, so we say y hat is the orthogonal projection of y onto u, and z is the component of y orthogonal to u, simply the orthogonal component. Now, we define L is spanned by u, so rather than u itself, we consider whole line containing the vector u, so that it is origin, then L will be the whole line passing and including u, like that. Okay. Now then we can write in this way. Y hat, the same quantity, can be written in this way. Projection of y onto L. So we call that way, we call the term the orthogonal projection of y onto L. The reason we consider such expansion is here, it is meaningful whether the angle between y and u is acute or obtuse. And for example, now u is given in this way and y is that direction, so that this angle is obtuse, then projection will be this point, and like that. Okay, so but now it is not on u, because u is the other direction. So a little bit confusing. So rather than a vector, even though later on we'll try to use projection to a vector, however, we have to understand that so that the projection is made onto the space spanned by the vector. Okay, so it is geometrically more meaningful. Okay. Okay, see this example. Y and u are given. Find the orthogonal projection of y onto u. Okay. Now, so part A, first we have to find here y equal y hat plus z. Now y hat is here alpha u. Now what is alpha? Alpha is y dot u over u dot u. Okay, y dot u is here 28 plus 12, and divided by u dot u, that is 16 plus 4, bottom is 40, top is 20, bottom is 20, top is 40, so it is 2. So here y hat is twice of u, and that is now 4 and 2, so that is 8 and 4. Okay, so we have a z equal y minus y hat. Y is 7 and 6, and y hat is now, okay, subtraction, 8 and 4. So we have here, that is minus 1 and 2. Okay, and so here y hat is this one and z is this one. This summation is the same as the given y. Write y as the sum of 2. Okay, so part B, we can, in fact, part A is asking this one only. So here y equal y hat, that is 8 and 4. And then z is minus 1 and 2. Okay, now find the distance from y to L. Here, it is useful to find the distance from a vector to a subspace. Now, line is made and a vector is given in this way, so that here, this is origin, and the projection is pictorially this point, so that is now z. So distance must be norm of z. So that's part C. So distance must be norm of z, the orthogonal component. So that is the same as square root of 1 plus 4, which is square root of 5. That's the final answer. Okay. Okay. Find the orthogonal projection of y onto U and write y as the sum of vector in span U and one orthogonal to U. So we want to get the decomposition. Okay. Again, we start with y equal, okay, start A here, y equal y hat plus z, and z equal, oops, okay, and y hat is alpha u, parallel to u, and u is same as y dot u over u dot u. Okay. Y dot u is 2 minus 12. That is 2 and minus 12. And u dot u, which is 4 plus 16. And so that minus 10 over 20, so minus half. So we have here y hat equal, so the projection itself, y hat is minus half, and u, which is now here, that is minus 1 and then 2. All right. Okay, minus 1 and 2. Okay. Now, we want to express y as the sum of two vectors. So the part B, we have to decide z, that is y minus y hat. Okay, y is 1 and 3. Subtract here, and minus 1 and 2. So that the top will be 2, bottom is 1. Of course, if we try to get distance, then again here, that is normal z, which is again same as square root of 5, right? Now we can expand the notion and general dimensional vectors. We'll deal with one more here, so that we have to find the distance. So we have to decide the z and norm of z. That's the goal. And in R3. Okay, here we have to find the v hat. V is projected to w. So the v hat is alpha w. Now alpha is same as v dot w, and w dot w is projected to w space. Okay, so that is 8 minus 12 and plus, okay, again minus, minus 24. Okay, and then w dot w, which is 4 plus 1 plus 9. So bottom is 14, top is here minus 28. Okay, that is minus 36. Okay, minus 26. So here we have minus 2. So here v hat is minus 2 times w, which is, now that is minus 4 and minus 2 and 6. Now z is v minus v hat. Okay, and that one minus this one. So the first one is 8, right? And then subtraction will make minus 10. Right, and then subtraction, that will be 2. Right? Okay, so here the distance will be, okay, distance will be norm of z, and that is same as square root of 64 plus 100 plus, now that is 4. Okay. that is 168. Okay, it'll be about 12, I believe. That is 12.9. Okay, it's almost 13. Okay, almost 13. Yeah, you can check it. Okay, now we'll continue in the second part. Thank you.